In a perfect world, when we use the Gauss-Jordan method, we would get unique solutions. But unfortunately, we may also get some dependent solutions, which means we're going to get an infinite number of solutions. We'll treat these systems exactly as before, but we'll need to use a parameter to help us see the infinite number of solutions. So let's take a look at another example. We'll work these out exactly as we did before, but we'll see some slight differences that we'll need to account for. So our first equation is 3x plus 5y minus z equals 0. The second equation is 4x minus y plus 2z equals 1. And the last one is 7x plus 4y plus z equals 1. That's in the proper format, so we can just drop that into our augmented matrix as you see down here below. We need to make sure that in the first row and in the first column that we have a 1, and here I see a 3. In the previous examples, we've been able to just leave it alone or maybe even interchange some rows, but the problem here is we're not going to be able to do that, because what I see, if we tried to interchange, we'd interchange and put a 4 or a 7 up there. That's not going to do us much good. So instead, what we're going to do is we're going to multiply the first row by 1/3 and put that in place of row 1. So 1/3 times the entries 3, 5, -1, and 0 gives us 1 5/3, -1/3, and 0. And then we're going to go ahead and put that into the first row. Now the disadvantage here is we've got fractions in the problem. Often, if I can avoid fractions, I try and do it. But in this particular case, we're just going to have to live with those fractions. So now I need to work with that entry that we just put in place, the 1, and we need to use that to help us put a 0 below it in the second row and in the third row. So what that means is we're going to need to take -4 times row 1 and add it to row 2 and put it into row 2, and -7 times row 1, add it to row 3 and put it into row 3. Notice because I have a 1 there, it's really easy to figure out what I need to multiply by, the -4 and the -7. So down below here, you see the -4 times the first row, the -7 times the first row, and then I'm going to add it to the second row or the third row. I'm going to have to work with some common denominators and things like that, but you can always use the frac key on your calculator to do a lot of these. So what I'm going to have to do now is to go ahead and put in place of row 2, 0 minus 23/3, 10/3, and 1. And into row 3, I'm going to have to put 0 minus 23/3, 10/3, and 1. So when I do that, I see it in the matrix up here. I've got the 1s and the 0s as I'm supposed to have. But now in step 4, I need to make the minus 23/3 in the second row, second column. That needs to be a 1 now. So I'll do that by multiplying row 2 by minus 3/23 and put that into row 2. When I do that, I see that my entries are 0, 1, minus 10/23, and minus 3/23. And I'll put that into my second row. Now in the next step, I need to go ahead and put a 0 below that 1. So to do that, I'll have to take 23/3 times row 2 and add that to row 3 and put the result in row 3. So here you see that worked out. And what's kind of interesting here is we get a row of 0s that now I'll put into row 3. Now this tells me something funny is going on here. So I'm going to jump straight to step 9 now, and I'm going to try and read off my solutions because there's no way I can use that last row to put 0s up here where I did before. So if I think about that, the last row of this matrix tells me that 0x plus 0y plus 0z equals 0. That's just the equation 0 equals 0. So what I'm going to do is I'm going to rewrite the first two rows back as equations. So my 1 5/3 -1/3 0 becomes x plus 5/3 y minus 1/3 z equals 0. And the second row becomes y minus 10/23 z equals negative 3/23. I'm going to go ahead and solve that second equation for y. And to do that, I'm going to have to add 10/23 z to both sides. So the second equation becomes y equals negative 3/23 plus 10/23 z. Now I'll substitute that second equation into the first equation and simplify. So x plus 5/3 times what had been y but is now negative 3/23 plus 10/23 z minus 1/3 z equal to 0. And if I now go ahead and solve that for x, I get x equals minus 5/3 times the quantity negative 3/23 plus 10/23 z plus 1/3 z. And when I simplify that, I see now that x is equal to 5/23 minus 9/23 z. The y is still what we had before, negative 3/23 plus 10/23 z. But now I have both x and y written in terms of z. So that means z is a parameter. So you can pick any value you want for z, which is reasonable for the problem, and you'll get different values or for x and y. So for instance, if I were to go ahead and pick z equal to 0, I'd know that x was 5/23 and y was negative 3/23. I could pick z to be 1 or 2 or 3, and I'd get other values for x and y. Since I can pick anything I want, there's an infinite number of possibilities for z. That means I get corresponding infinite numbers of x's and y's. And that's why we say that this system has an infinite number of solutions, because I can pick z to be anything I want.